Hi, so welcome to chapter 4, lecture 4 of this class. It's about motion in two and three dimensions. So what we're going to do at first is going to be very similar to the kinematics equations that we derived last week. In fact, it's going to be almost exactly the same, using your same skills that you picked up last week. You just need to dissolve vectors or decompose vectors into their x and y components instead of worrying about only one dimension. And then the second part is going to be a centripetal or center seeking acceleration, which is just the motion of a particle or an object going around and around in a circle. So, and then we're going to close off with a little bit on uh, word on velocities and accelerations in different moving reference frames. So let's get started. The first thing that we're going to derive is an vector form of all of our kinematics equations and like all of our one-dimensional things that we've been doing up until now. So we have r of t instead of x of t, which is going to be x of t in the I direction plus y of t in the j direction plus z of t in the k direction. So what this is it's just a vector showing you the position of something that you're looking at in three dimensions. So instead of just telling you how far out you are in I dimensions in the x-axis like we would before, it tells you how far out we are in I in the x direction, how far out we are in the j direction, which is the y of t, and how far out we are in the k direction, which is z of t. So this is pretty self-explanatory. It's just you have Cartesian coordinates in x, y, and z axis. And then if you have a vector that has x of t, y of t, and z of t, then it's just going to tell you its position in your Cartesian coordinates. So right here is z of t high, uh, x of t to the x-axis, and y of t on the y-axis. So a that gives you a point P at some area r of t, at some vector r of t. So when we take the derivative of this dr dt, then that just gives us dx dt I plus dy dt j plus dz dt k, which is equal to vx of t I plus vy of t j plus vz of t k. So what you notice is that vx, vy, and z are all independent of each other. They're all pointing in different directions, and the way that you derive or derivate or take the derivative doesn't change anything based on the vectors. So you have x, y, and z in their x, y, and z directions. And then when you take the derivatives, vx, vy, and vz are still all in the same direction, all in the x, y, and z directions respectively. So this is equal to the velocity vector. So dv dt equals d vx dt I plus dv y dt j plus dv z dt k, which is just going to be ax of t I plus ay of t j plus az of t k. And notice again that none of these depend on each other, so they're all independent in the different directions. So this is a of t. So for example, if we have, so just to do a quick example, it's probably, I think it's something on your homework, but it should be obvious. So if you have r of t is something like 3t squared minus 7t I plus 4t to the fifth k plus 7z, then the velocity vector v of t would be the derivative of everything in front of the I in the I direction. So 3 times 2t minus 7I plus 4 times 5t to the fourth k plus 0, or oh, I made a boo-boo. I was saying k would be in the y direction when really it should be j in the y direction. So j, k plus 0 in the k direction, because the derivative of a constant is going to be 0 because the constant never changes. That's what it means to be constant, so there is no change in the number 7 over time. And then a of t is going to be the derivative of v of t, which is going to be 6 times 1 minus 0 I plus 20 times 4 t to the cubed j, which is just going to be equal to 6i plus 80 t cubed j. So, like I said, this is just doing basic derivatives, except for instead of doing treating everything as its own variable, or treating everything as one-dimensional, you go according to each direction first. So you take the derivative in all the I directions, you take the derivative in all the j directions, and you take the derivative in the k direction. So the k gets knocked out immediately as you go to velocity, but the I and j directions still have some components left in when you get to acceleration, when you take the double derivative of position. So in addition to all of this acceleration and stuff like that, there is also displacement, which is the change in position, which is going to be equal to x final t minus x initial t in the I direction plus y final t minus y initial t in the j direction plus z final t minus z initial t in the k direction. So that's pretty simple. There's a problem in the textbook that utilizes it well, but or tells you gives you a good example of what that means. So basically, if you have a globe, if you're looking at the globe, if you're looking at the Earth, then you have one particle or one person at a position on the North Pole, and then somebody on the prime meridian, some degrees south, yeah, some degrees south of the prime meridian, which is pointing in the x direction, or yeah, let's just call it x direction. It can be the east direction, it can be the west direction, it can be some combination of them. So as long as you're looking at this two-dimensional slice of the globe, then you have these two vectors, and you want to find the displacement vector between the two of them. So what you would do is you would just take x r initial is equal to uh 0 west, yeah, let's just call this west, plus uh radius of the earth north, and then our final is going to be equal to radius of the earth times cosine phi in the west direction plus or cosine negative phi in the west direction plus sine of negative phi in the north direction equals RE cosine phi, because like I said before, cosine is an even function, which means that the angle, when you put a negative angle into it, it gives you the same value as when you put the positive version of that angle in. While sine is an odd function, which means that if you put negative angle in, it gives you the opposite of the positive angle. So minus sine phi in. So delta R is going to be equal to RE times cosine phi west minus sine phi north minus RE north, which is just going to be RE times cosine phi west minus 1 plus sine phi north. So that's just going to give you your displacement vector, the change between the two vectors in terms of one or the other, in terms of the radius of the Earth and the angle of your second vector. So, remember a few minutes ago how I was saying that it looked very similar uh, to the one-dimensional case, because if you have R of t, it's just going to be x of t I plus y of t j plus z of t k, and then the velocity is just vx I plus vy j plus vz k, and the acceleration is ax I plus ay j plus az k. You see how each of these is broken up into only mattering in their own direction? What this means is that if you walk out in some direction to the right, and you're moving and you're accelerating or you're doing anything like that, then none of that is going to matter when you're talking about the direction that you're moving uh, to up, or the direction you're moving into the sky. So because all of these are independent of one another, when we write out the kinematics equations, we can just break it up into its components instead of worrying about how each component the X, Y, or Z interferes with the other components. So, for example, we have our kinematics equations. X of t equals x naught plus v naught x t plus 1/2 a t squared. Vx of t, v naught x plus ax t, x of t equals x naught plus vx average t, and vx squared of t equals v naught x squared plus 2ax x minus x naught. So these are our equations that we came up with last time, right? So these are the equations of motion that we came up with in one-dimensional uh, kinematics. And what happens is that these are completely independent of the y and the x variable, or the y and the z variables. They're only dependent on all of the x variables. So the velocity in x and the acceleration of x, they're completely independent of y or z because it's only telling you about the motion in the I direction. So just a second, I'm seeing if it lets me copy paste. It does not. So what this also means is that we're talking about velocity in velocity and accelerations in a two-dimensional system where y of t is what we're worrying about instead. Then instead we can use the equations y of t equals y naught plus v naught y t plus 1/2 ay t squared. Vy of t equals v naught y plus ay t. Y of t is again v naught y naught plus vy average t, and vy squared of t is equal to v initial y squared plus 2ay x y minus y naught. And then same in the k direction. Except sub in z for y or x, where z is just like the velocity in the z direction, the velocity or the acceleration in the z direction, and so on and so forth. So, like I said, incredibly similar to what we did last week. it's going to be very simple for it's the main problem that I foresee happening is people having trouble breaking down velocities or breaking down velocity vectors into the x and y components. Otherwise, you should be fine. So in two-dimensional motion, in projectile motion, what we have is a special case where uh, we only care about the x and y directions. So it's uh, motion in a two-dimensional system with x and y, where you shoot, say, a cannonball and it study the path of its motion. So you can shoot a cannonball, or you can hit a baseball, or just throw something, throw a paper airplane. Though that isn't a very good example because it relies incredibly on air resistance, and we're still assuming that air resistance doesn't exist. So in projectile motion, our assumptions are that AY equals negative G and AX is equal to 0. So there is no acceleration in the y direct, or there is no acceleration in the x direction, but there is gravitational acceleration in the negative y direction. So when we have our equations like this gives us kinematics equations x of t equals x naught plus v naught x t plus 0 t squared gives you x naught plus v naught x t. And then v x of t is equal to v naught x plus 0 times t equals v naught x. So the velocity never changes when you're doing a simple projectile motion problem in the x direction. So that's our equations for in the x direction. You can also get the other two kinematics equations by just looking at them, but delta v squared equals negative 2a delta x is also going to give you 0 equals 0. And x of t equals x naught plus v average t is going to give you the same thing as v naught xt, because v average equals v final equals v naught x. So for y of t, you have something a little more complicated, where y of t equals y naught plus v naught y t minus g over 2 t squared, and then vy of t equals v naught y plus or minus g t uh, y of t is equal to y naught plus v average y e, and then vy squared equals v initial squared minus 2g y minus y naught. So the y components are a lot more complicated than the x components, but it is always going to have the same acceleration if you're on Earth, or if you're on Mars, you're going to have a different gravitational acceleration, but you're going to follow the same structure, where instead of g being 9.8 meters per second squared, it would be some other number. So at this point, I'm going to go to a different share and share, okay, a part of the textbook, which tells you a problem-solving strategy for projectile motion, which is to resolve the motion of the horizontal and vertical components along the x and y axis, the magnitude of the components of displacement along the axes are x and y. The magnitudes of the components velocity are vx equals v cosine theta and vy equals v sine theta, which is just what we got from decomposing vectors earlier, I think in chapter 2, where v is the magnitude of velocity and theta is its direction relative to the horizontal. And then treat the motion as independent one-dimensional motions, one horizontal and the other vertical. Use the kinematic equations for horizontal and vertical motion presented earlier. Solve for the unknowns in the two separate motions, one horizontal and one vertical. Note that the only common variable between the motions is time t. The problem-solving procedures here are the same as those for one-dimensional kinematics and are illustrated in the following solved examples, which I won't go through all of them, but I will go through one or two, and then recombine the quantities of the horizontal and vertical directions to find the total displacement s and velocity v. Solve for magnitude and direction of the displacement using displacement s equals square root of x squared plus y squared, and phi equals arctangent of y over x. V equals v square root of vx squared plus vy squared. And then while we're at it, I also want to point out this diagram where it shows us the velocity and it shows us motion diagrams. I don't remember if we've gone over those in this class, but it shows us motion diagrams for the horizontal and the vertical components and shows us how they interact. Let me annotate. Come on, Zoom. There we go. Show how they interact. So horizontal component with constant velocity, the horizontal component just keeps going on and on at the same velocity. It travels the same distance over a given time, the entire time that it's moving. But the vertical component, if you start with a v naught y, then positive v naught y, then it goes up and up and up, but it's losing acceleration, or it's losing velocity because it has a negative acceleration and a positive velocity. So it goes up, and then it hits a point where it doesn't accelerate at all, and then it starts going down and accelerating in the downward position. So when you look at the total velocities, you start out with v naught y and v naught x. The velocity in the y direction changes over and over again, but the velocity in the x direction stays exactly the same. So that at its peak, the velocity here is only the initial velocity in the x direction with no velocity in the y direction. So you go across that, and then you go down farther and farther, and then the velocity in the y direction starts changing, but the velocity in the x direction stays the same. Yeah, so that's the generals of projectile motion. I'll just go through a single problem to try to get you used to it. So uh, for that problem, let's see. Uh, let's say that you have a velocity v naught. You're a tennis player and you're hitting with a velocity at v naught at some angle above the x-axis. And you want to know what time it will get, and it goes off into the stands, some distance uh y final over the initial y initial equals 0. So it goes off into the stands at some distance above your initial position, and you want to know what time it takes in order to do that, and how far out uh that is, and how uh what the final velocity is going to be like. So if you do that, then you're going to need to write down initial all of your equations in this, all of your variables in this equation that you know and that you don't know. So you know Vx equals V naught Vx equals V naught x, V naught x equals V naught cosine theta. Uh, I should call this, instead of theta, I'm going to call this phi just to be consistent with the book. Uh, 8x equals 0, x naught equals 0. Uh, time is unknown, and x final is unknown. Whereas for v naught vy, we have vy equals v naught y minus gt, v naught y equals v naught sine phi, ay equals negative g, y naught equals 0, t equals question mark, and y final equals question mark. So, oh, y final equals y final. That's one of the knowns that we do know. Sorry, that was silly. So we use the equation y of t equals 0 plus v naught sine phi t minus g over 2 t squared. So y final equals y final. So g over 2 t squared minus v naught sine phi t plus y final equals 0, where I just subtracted this from both sides, the g over 2 t squared minus v naught sine phi to get 0 on the left-hand side, and g over 2 t squared minus v naught sine phi plus y final on the right-hand side. And then I switched those sides because that's the convention. Uh, so in order to solve for t, we use the Pythagorean theorem. T equals negative v naught sine phi plus or minus the square root of v naught squared sine squared phi plus minus 4 times 1 times g over 2 all over 2 times g over 2. So you just solve for that, and that's going to give you a value, and we're going to go with the farther value because as we look at this motion diagram, as we look at this parabola, or not motion diagram, just graph of y versus x, as we look at this graph of y versus x, it first goes up and then comes down at a later time. So we want to use, instead of in the plus or minus, is going to give us either the minus is going to give us a smaller time, and then the plus is going to give us the time that it takes to go all the way down, to start falling down and hit that height again. And then if you don't remember, the way that we got that is if we have a formula ax squared plus bx plus c equals 0, then the way to solve for that x values is that x equals negative b, whatever's in front of the x coefficient, or whatever's the coefficient for x to the 1 power, plus or minus the square root of b squared minus 4 times a times c all over 2a. So we did that for t, and we were able to find the time that it took to get there in terms of the initial variables and the initial angle. So we can also just find x of t by multiplying all of this by v naught of x, which I'm not going to do because it will just make it ugly, but x of t is just going to be v naught cosine theta cosine phi v naught cosine phi times that entire expression for t right there. And then to find the final value of velocity, we solve v final x equals v initial x, and then, or yeah, vx equals v initial x, and vy squared equals v initial y squared minus 2g y minus y naught equals v initial y squared minus 2g y final equals so vx equals v naught cosine theta or cosine phi, and vy equals v naught sine phi, and yeah, v naught y equals v naught sine phi. So this vy squared equals v naught sine phi minus 2gyf. So when we plug this into our v squared, or v is going to be vx squared, the square root of vx squared plus vy squared. And this is going to give you equal to v naught cosine phi squared plus v naught sine phi squared minus 2gyf is equal to square root of v naught squared minus 2gy final. Because if you remember, cosine squared phi plus sine squared phi, I think I accidentally went over this in class when I said I would just leave it alone, but using the Pythagorean theorem, cosine squared phi plus sine squared phi is equal to 1. So v naught squared cosine squared phi plus sine squared phi minus 2gyf is going to give you this expression right over here. Okay, so that ended up taking a lot longer than I expected, but it is useful to know. So we are going to talk, this is all you need to know for projectile motion, but I'm going to talk about a little bit about how we talk in the, or how we solve for problems in the special case where y initial equals y final. Because in that case, then we have y of t equals y final equals v y naught plus v naught y t minus 1/2 gt squared. Then y final equals y initial, so subtract by y initial on both sides. So 0 equals v naught y t minus 1/2 gt squared equals v naught y, factoring out the t, minus 1/2 gt squared, or gt, times t. T uh divide by t on either side. 0 divided by t is 0. So we get equals v naught y minus 1/2 gt. So 1/2 gt equals v naught y, adding on the other side, t equals v naught y times 2 over g is equal to v naught sine phi, 2 v naught sine phi over g. Yeah, I got that right. So this is called the time of flight. So it's how long the ball is in the air when you're talking about a special case where the final height is the same as the initial height. So in the special case where you're on like a straight ground and you're seeing just how far it goes off in the how far it's in the air and how far it goes off. So uh the trajectory is another thing that we use where uh we just substitute in for x of t. So the trajectory tells us what y of t is in terms of x of t. And does it is going to it doesn't matter whether or not you're going to end up at the same height as you do beforehand, like it does with the range and the time of flight. But x of t is equal to v naught x t. Therefore, t is equal to x over v naught x. So we plug this in to our y of t equation. Y of t equals y naught uh, y naught. Oh, this is also plus x naught of t, but this is going to go to 0. And so is this. We're going to assume that it starts at position 0, 0. So that's going to be v naught y t minus 1/2 gt squared equals v naught y times x over v naught x minus 1/2 g times x over v naught x squared, where this is going to be equal to v naught sine phi over v naught cosine phi x minus 1/2 g over uh, cosine phi squared times x squared, which is going or 2g over v naught squared cosine squared phi squared. So this is going to be equal to tangent of phi x minus 1 g over 2 v naught squared cosine squared phi times x squared. And then this is going to give you the entire This is going to give you the shape of the projectile motion. So y is dependent on x as a parabola with the coefficient in front of the x squared term being g over 2 v naught squared, and the coefficient in front of the x term being tangent of phi. So if this is the case, uh, then we can for our range, which is how far out in the x direction it goes, we go back to the assumption that y naught equals y final equals 0. And if we do this, then we get 0 equals tangent phi x minus g over 2 v naught squared cosine squared phi x squared. We factor out the x, tangent phi minus g over 2 v naught squared cosine squared phi x times x equals tangent phi minus g over 2 v naught squared cosine squared phi times x. So gx over 2 v naught squared cosine squared phi equals tangent of phi x equals 2 v naught squared cosine phi over g times tangent of phi, which is 2 v naught squared sine cosine over g, which if you remember your trigonometric properties, um, 2 sine phi cosine phi is equal to sine of 2 phi. What are you doing? Okay, just a second. There we go. So this gives us x equals v naught squared sine of 2 phi over g. So this is the range. This is how far it will go if y naught equals y final equals 0. Okay, so hopefully that wasn't too confusing. This is a useful thing to know, uh, especially if you're doing projectile motion. And it just looks a little crowded in this, but that's how it goes. So for centripetal force, we're done with projectile motion for the moment, and now we're going to go on to centripetal force. So for centripetal force, you have some object moving in a circle with R1, R, sorry. So you go from this point with some velocity v and some distance along the circle r to this point with the same velocity v and the same distance along the circle r. But you uh so centripetal motion in its most simple case assumes that the velocity is going to be constant because it's hard to keep a centripetal motion if there's some outside force accelerating it that's causing, or if there's some outside force that's accelerating it in the tangential direction. So in the direction tangential to the circle instead of just into the center of the circle. But uh, for our most basic version, we assume that velocity is constant. Uh, or not even velocity, because there's a difference, right? Speed is constant. Velocity is tangential. That means that it doesn't point anywhere towards the center or away from the center of the circle. Far it all goes to the side of the circle like you see in this diagram. And our radius is also constant because if the radius isn't constant, then we're not talking about a circle. We're talking about an ellipse or like a parabola or any number of different equations. So if this is the case, if speed is constant, velocity is tangential, and radius is constant, then we have some angle which is a right angle, so it's 90 degrees between the radius and the velocity at any given time, which means that when we make a triangle, out of radius, uh, of the radius after some time, delta t, or the position vector after some time versus the initial position vector, and we make a triangle connecting those two, delta r, the difference in displacement, then that is going to be the same, a similar triangle to v of t and then v of t plus delta t. So that's going to make, these are going to have the same angles between them. So delta v So let's go a little more specific with these derivations than they do in the book. But uh if theta r equals theta v, so this angle of the triangle uh for r is the same as this angle of the triangle uh for the v triangle, then the delta r over r is the same thing as delta v over v. So delta v is going to become uh v over r times delta r. So why do we care? We mostly care because if there's some sort of acceleration, or if there's some sort of if there's some change in the velocity, even if it's not changing speed, it is changing direction, that means that there has to be some sort of acceleration. And we can take that by taking delta v, delta t, and see what the magnitude of the acceleration is, equals vr delta v, or delta r over delta t. So as the limit of delta t goes to 0, this becomes dv dt equals acceleration equals v over r dr dt equals v over r v equals v squared over r. So the magnitude of the acceleration, in order for this to be true, in order for these assumptions to be true, the magnitude of A must be v squared over r. So we are making these assumptions, not we are making these assumptions on the left, not the assumptions that at acceleration is v squared over r. So you need to work from these assumptions in order to find in order for it to be true that the acceleration is v squared over r, not the other way around, which is what a lot of people mistakenly do. They try to um, make it so that a equals v squared over r, therefore the radius is changing in some way in order to satisfy the assumption that a equals v squared over r, when really it's the opposite way around. Radius has to be constant, therefore a has to be v squared over r. And then this is a consequence. And then another consequence is that the acceleration must be pointing into the center of the circle, because V is changing, velocity is changing, but the magnitude of the tangential velocity doesn't change. Therefore, all of the magnitude of the acceleration has to be perpendicular to the tangential velocity. Therefore, all of the acceleration has to be pointing into the center of the circle. And yeah, you can do some basic equations with that. They're in the homework. If you have any questions about the homework, feel free to ask me, but I'm not going to go through that right now because it is very basic questions. And then another way that we can describe centripetal motion is that with constant acceleration, with constant velocity in the v direction, is that or constant velocity in the tangential direction, sorry. Let me just get a glass of water. Another way we can describe the position over time of centripetal acceleration of centripetal force with acceleration in the towards the center seeking acceleration, which is what centripetal means, is and constant velocity, is we can say R of t is some constant R naught cosine omega t I plus R naught sine omega t k, or not k. This is the second time I've made that mistake today. J, where omega t is describing the angle subtended by the particle, by the object over a given time. So this is a pretty lousy drawing of a circle, but what's happening is that omega t at any given time is going to give you the angle that it makes with the x-axis. So therefore, you can decompose it into r naught cosine phi and r naught sine phi, which is r naught cosine omega t and r naught sine omega t. So if this is the case, then v of t is going to give you uh yeah, negative omega times r naught sine omega t I plus r naught plus omega times r naught cosine omega t j, using the chain rule. And if you don't remember the chain rule, definitely reach out to me because it is something that I'm very likely to put on a test at some point. And then A of t equals negative omega squared r naught cosine omega t I plus or minus omega squared r naught sine omega t j, which is just equal to negative omega squared r naught cosine omega t I plus r naught sine omega t j equals negative omega squared times your initial r vector. So two things that we can tell from this. So from this we can tell two things about the omega squared. The first is the definition of omega squared, or of omega. Omega equals 2 pi times the frequency equals 2 pi over period, which is just the definition of what happens when you have a sine wave of some constant 2 pi over period times t. That's just going to be what happens when you're talking about that in terms of variables that we have and like mathematically in order to keep the units constant, there has to be some sort of, this has units of seconds, this also has units of seconds, so these two units cancel each other out. And I don't know if you remember this for math class, you should have learned it at some point, but this is just uh every time t equals n times t, some number some integer n times t, then this is going to be this value 2 pi over t plus t is going to go to n times 2 pi. Ew. Which means that every time you go through the period t, big T, then you're going to go through the entire cycle of the sine wave from like 0 to 2 pi, and then from 2 pi to 4 pi, from 4 pi to 6 pi. So the period just tells you how often you start repeating the cycle. So that is what omega is in terms of mathematically. We also found that A equals negative omega squared r, which is negative omega squared r in the r hat direction, where r is just the unit vector. And we know that this is going to, or equals omega squared r in the negative r hat direction, which means that it's just pointing along the center of the radius. So if this is the case, then we know that A equals V squared over R in the negative R hat direction. So omega squared R equals uh, V squared over R. Therefore, uh, omega squared equals V squared over R squared, or omega is equal to V over R, which is our physical consequence of using this equation. So this is a mathematical consequence, and that's the physical consequence. So there's something about non-centripetal or circular motion that isn't completely along, that doesn't have a constant velocity. And then I don't know how physical that is. That seems like a pretty hard thing to set up. But I'll leave you to read the book if you want to do that. I'm not going to put anything like that in the midterms because it's not super use, or it's not the most immediately reason the most immediately pressing thing that you need to learn. The first thing you need to learn is centripetal acceleration, and then if you learn that, then you can move on to non-center seeking acceleration. But the last thing we are going to talk about, and I apologize for this taking so long, is velocity in different reference frames. So for example, if you are going along a if you are going along in a train that's moving at 10 meters per second, and then you start walking at -2 meters per second relative to the train, then from an outside observer in the on the earth on the platform, it looks like you're walking at a velocity of 8 meters per second. So the equation that you uh, use in order to calculate this is that V of the person with respect to Earth is equal to V of the person with respect to the train plus V of the train with respect to Earth. So, or this can be person, or this can also be point. Uh, so you have this equation. This tells you how to find the velocities because you're going already going at 10 miles or meters per second with respect to the Earth. Then any additional movement that you will make will look like it's adding 10 meters per second with respect to the Earth when you're really only going 0 meters per second with respect to, or 0 meters per second, or -2 meters per second with respect to the train, with respect to the system that you're moving in. So this is going to be -2 meters per second, and then this is 8 meters per second. So another way to write this is that P equals position, S equals stationary reference frame. So the position of the Earth, say, or whatever you're uh not stationary, because everything's moving with regards to each other. S equals reference frame that we're curious about. S prime equals reference frame uh moving with respect to S, i.e. the train, and then R P S equals R P S prime plus R S prime S. Where this is uh position uh in S prime, and this is position in of S prime in S. So for example, if we're talking about uh two different reference frames, one which starts at a door and the other one which starts at a table, then the position uh in the table reference frame would be the same as the position in the door reference frame plus the displacement between the door and the table. I hope that makes sense. That's basically what's just going on here. So this is probably a very formalized way to do this, but if you think about it, it isn't. It's just something that you have to think about until it makes sense to you. And then if this is the case, if this is true, then that leads to VPS equals RPS prime. Oh, not RPS prime, VPS prime plus VS prime S, which is what we did over here, what we did to the left. And then A PS equals V P or A PS prime plus A S prime S. And then in most of the systems, we're going to be looking at uh because uh most of the systems we're going to be looking at aren't going to have any acceleration of S prime relative to S. So this is just going to have the same acceleration in S prime as it does in S in your stationary system or your reference system. And then another thing that we can say about this is that VPC is equal to VPA plus VAB plus VBC, where you can just stack these reference frames so you can see how the person moves in A, and then how A moves in B, and then how B moves in C, and that's going to tell you how the person moves in C. Okay, so uh, the velocity of a car, let's do one example and then close out. So the velocity of the car with respect to Earth uh, is going to be equal to 80 kilometers per hour in the I direction. And there's also a truck coming along. A V truck equals negative 70 kilometers per hour in the J direction. So basically what you're seeing here is a car, that's a pretty bad car. It's going along up here, and then there's a big truck going along down here. And you want to be able to tell what their velocity of the car is or appears to be relative to the truck. So VCT is the velocity of the car to in respect to the truck equals VCE plus VET equals VCE minus VTE. Because if we're looking at a problem, if we're looking at the truck moving through the earth, then it's going to be moving in the opposite direction at the same magnitude as if we're looking at the earth moving through the truck or moving along the truck. So VCE minus VTE equals 80 kilometers per hour I minus negative 70 kilometers per hour J equals 80 kilometers per hour I plus 70 kilometers per hour J. So what this means is it looks like to the truck, you are coming towards it at some velocity and at some angle phi. So this is, you're coming towards it at 80 kilometers per hour in the x direction and 70 in the y direction. So the the magnitude of VCT, I keep pressing a button that I shouldn't, is equal to square root of 80 squared plus 70 squared equals 106 point kilometers per hour. And then phi is equal to arctangent of 70 over 80 equals 41.2 degrees north of east. So notice that even though you're both moving in cardinal directions, to the truck, because it's moving towards the same space in you, same space as you, it looks like you're moving towards it at some velocity and at some angle, even though you're both moving like to the north or to the east or to the south and to the east. From the perspective of the truck, it looks instead like this. Okay. Well, that ended up taking a while. I thought it was going to be a pretty simple explanation, but if that's the case, then I'll just be here for any questions that you have, and we'll wrap up right now. All right. Thank you very much. Uh, I'll stop the recording now.